So the second question in this chapter, Gauss's law, question number 2. So it's the following. We have a coaxial and cylindrical shell, which looks something like that, where the inner radius is A and the outer radius is B. So if I draw it, it's like A and B. And the length of this thing is L, capital L. And it's, so let me write it, coaxial and conducting cylindrical shell. Inner radius is A, outer radius is B. And here, the length, this L, is much bigger than B. So we are interested in the length of this object, where it is much bigger than both A and B, and also the other distances that we will consider. Oh, and in reality, this is something like there is an inner positively charged conductor, and we basically, which is very thin, and outside we put equal amount, maybe with pink, negatively charged. So if this is like plus Q, this is like minus Q outside. So the question is the following. Find out the magnitude of the electric field. E magnitude is equal to what? For two different cases. One, where the radius is between A and B. So A and B. Find out the electric field between these two conductors, like somewhere around here, for instance. And in the second question, it is asking us to figure out the electric field at a point which is far away from both of that, which is where R is bigger than B, but still much smaller than L. So that's basically it. Okay, so the first part of the question is kind of simple, and it looks like the previous case, but remember what the idea of the Gauss's law was? And in general, Gauss's law is the following. Maybe I should write here. EdA for a closed Gaussian surface is equal to the enclosed charge inside the Gaussian surface divided by epsilon 0. Okay, so it's two things. First, you would like to find out the appropriate Gaussian surface so that you don't have to do this integral. You can just take E out of the integral for the particular area that you're interested in. And then you want to find out the closed, the charge on that closed Gaussian surface, enclosed charge. So it's two things. Find out the best Gaussian surface and then use the Gauss's equation where Q is the Q enclosed inside that Gaussian surface. Okay, so what is the Gaussian surface for this particular problem? It is the following. So we have this, the inner shell, and then there is the outer shell. And I'm going to draw that by the other color, the outer shell. And let me even draw that. And this is the inner shell. And remember that this is like positively charged, and these guys are negatively charged. Okay, so this was the original question, and you remember that in part 1, it's asking us to find out the electric field at a distance where R is bigger than A but smaller than B. So the best Gaussian surface for this is the following. You basically choose this guy, where remember that this R is smaller than B but bigger than A. So it's bigger than A, but as you can see, it's smaller than B. So it's somewhere in between where R is the variable, okay? And if you choose this Gaussian surface, which is exactly a cylinder, of a length of like L, but this L is smaller than the capital L, right? It's some portion of the cylindrical shell. But remember that this L is a huge length compared to these both A and B. Okay, so this is the Gaussian surface. So this Gaussian surface, there are three parts. Right. First of all, you can see that this is like a uniform electric field, because if this is long enough, and if you take some portion of that, the electric field, maybe I should use that, is going to be from plus to minus. So it's going to point something like that, always like this, right? From plus to minus. And you can see that at any point along this pink Gaussian surface, both the area vector, the side part of that, and the electric field are along the same direction. And for this surface and that surface, like let's say the top and the bottom of the cylinder, it's going to be tangential. So that's why this is a nice Gaussian surface. And if you look at it from this perspective, maybe it's better to see it. So let me do it like this. And let me give first name to the three names. So the general equation for the Gauss's law is EdA is equal to Q enclosed over epsilon 0, right? And this dA is, the EdA integral is taken for the whole pink Gaussian surface. And it has three parts, right? It has this side part, A1, another side part, A2, and it has this lateral part, which is A3. So that's why this integral can be decomposed into three different ones, right? EdA, now it's not closed. The first one, let's call it A1, plus another integral, EdA, right? Obviously, there are all these vectors. A2, dot product, plus, now I have E times dA for the third surface. Okay, so if I draw this and from this perspective, it's going to look like this, right? Okay, so the electric field goes from, and this is the inner part, from plus to minus. So the electric field looks like that, right? This is like E, and from here it's again from plus to minus. Remember that inside I have a cylindrical shell, which is positive, and outside it's negative. So that's why it is from inside to outside like that. Okay, so I hope this way of drawing is kind of helpful. And this side is A3, right? Both here. So that's like A3 vector, and this is like A3. And A2 and A1 is like this. A1 is like left one. This is like A1. This is like A1, right? And this is A2. You see that the angle between the electric field and A2 and the angle between the electric field and A1 is 90 degrees. So that's why this dot product, so the angle between the two is 90 degrees. Since this is dot product gives you cosine of 90, this doesn't give you anything. It just goes away, right? And the same thing is true for the second Gaussian surface. This side, which the 90 degrees, again, cosine of 90 degrees, and you get 0 again. Now the third one, you see that for both cases, they're both pointing downwards here, and they're both pointing upwards here, and that's why the angle between the two is 0. And that's why this is cosine of 0, which is 1. So the only contribution comes from the third surface, and hence, the left-hand side of this equation, the Gauss's equation, is now E goes out of the integral, right? And this is the third one, because at any point on this surface, the electric field is the same, so you can just take it out. And this is dA. And this is nothing but A3, right? You just integrate all the infinitesimal dAs and you get the whole area is equal to Q enclosed divided by epsilon 0. And now the question is, what is the enclosed charge on this Gaussian, the pink surface, right? And remember that the charge is related to how large this thing is. So there are two things here. What is A3 and what is enclosed charge, right? So let's start with the easy one. What is A3? A3 is, let me write it here. A3 is the area, which is, remember that this, the lateral part is the circumference of the circle times the length, right? That's the area of the side part of a cylinder, so that's 2 pi r, the circumference, times the length, L. Remember that this is small l. That's A3. And what about the charge? The total charge, assuming that the total charge is Q, where the length is L, this is some portion of that, right? Small l. So Q enclosed, and the distribution is like, it's homogeneous in this direction. If its length is L, it's going to be proportional to L, right? And in general, we know that it's like lambda times L. And lambda, remember, is total Q divided by the total length. And hence, this is going to be lambda, which is Q, divided by total length times small l. Now we are ready to write down this, because this is E magnitude. So it is E magnitude times A3, which is 2 pi r times L, is equal to Q enclosed, which is Q divided by capital L times small l divided by epsilon 0. Now you see L goes away. The electric field should not depend on the Gaussian surface that we choose, because we're just using an arbitrary Gaussian surface to figure out what the magnitude of the electric field is. So you can take this 2 pi r in the bottom, in the denominator, so E becomes, the magnitude of E becomes Q divided by 2 pi r comes here, 2 pi times epsilon r and L. So R goes here and L is already here, right? So this is the magnitude of the electric field for this question. Thank you.